Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying how to find particular solutions to non-homogeneous equations, specifically second-order linear equations with constant coefficients and a trigonometric forcing function. So let's set up the situation we're going to be studying. We have a linear second-order differential equation with constant coefficients, and the forcing function is going to be some sort of combination of sines and cosines that have the same period and the same phase shift. So we have a second-order linear differential equation with constant coefficients on the left, and our forcing function on the right are sines and cosines with the same period and the same phase shift. Now, if we only have one of these, okay, for example, we only have a sine or we only have a cosine, that's not a big problem. Just imagine that one of these k sub 1 or k sub 2 are 0. Now, what if you have sines or cosines that have a different period or a different phase shift? Simply consider them separately using the superposition principle. The real point here is that if you have a sine and a cosine, you don't necessarily have to treat them as separate terms through the superposition principle. If they have the same period and the same phase shift, you can in fact tackle them at the same time. So here we have our general linear second-order differential equation with constant coefficients and some sort of trigonometric forcing function where the sine and cosine have the same period and the same phase shift. We're going to adopt the same general idea we used before. Now, if y happened to be some sort of combination of sines and cosines with the same period and phase shift, then its derivatives would also be sines or cosines with the same period and with the same phase shift. Now, because the derivatives produce both sines and cosines, right? The derivative of sine is cosine, and then the derivative of that would be negative sine. And similarly, if we started with a cosine, you can't really just suppose, well, why don't I just start off with a sine function if I want to produce a sine function? And why don't I just start off with a cosine function if I want to produce a cosine function? Because the derivatives will go back and forth between the two, if you're only looking for sines or you're only looking for cosines, your particular solution might still need both. So we set our particular solution to be some multiple of a sine and some multiple of a cosine with this same period and phase shift. Well, here's the first derivative of that, and here's the second derivative. Notice that this omega factors out from the chain rule each time you take a derivative. So here we have our differential equation, our proposed particular solution, its first and second derivative. So we take all of those and substitute it into the differential equation, producing a times yp double prime, which is all of this, plus b times yp prime, which ends here, plus c times yp. Now this is supposed to equal k1 sine omega x plus phi plus k2 cosine omega x plus phi. So naturally what we want to do is collect together all of our sines and collect together all of our cosines. So here was our differential equation, here was our proposed solution. Once we collect together all of our sines and cosines, having substituted it into the differential equation, we would end up with this right here. Therefore, we conclude that the coefficient in front of the sine on the left must equal k1, and the coefficient in front of the cosine on the left must equal k2. So c minus a omega squared times a minus b omega b must be k1, and b omega capital A plus c minus a omega squared times capital B must be k2. So here was our differential equation, our proposed solution, and we've determined that if this y sub p really is going to solve this, we would need both of these to be satisfied. Note, however, that little a, little b, little c, k1, k2 should all be known to you, as should omega. These should all be things from the original equation. The only unknowns down here are capital A and capital B. So we have two equations and two unknowns. We can solve that. And it does have a unique solution given by A is this quantity here and B is this quantity right there. Okay, so with our differential equation, with this forcing function and our proposed solution, we've determined that if we let capital A and B as given here, well then y sub p will in fact solve the differential equation. However, what would happen if b is 0 and c is equal to a omega squared? Well, if b is 0 and c is equal to a omega squared, the denominator here would be 0, and this would not, in fact, be a valid solution. So what do we do if c happens to equal a omega squared and b happens to equal 0? So we've got ay double prime plus by prime plus cy equals 0. Let's just consider the homogeneous case first. Okay, now assuming b is 0 reduces it quite simply to ay double prime plus cy equals 0. Substituting in c is equal to a omega squared, and we end up with this, ay double prime plus a omega squared y equals 0. Since a is a constant, which isn't 0, we can divide it out, and we end up right here. This is a second-order linear equation with constant coefficients. Okay, so what we do is we find a fundamental set of solutions by solving for roots of the characteristic polynomial. R squared plus omega squared should equal 0. This very quickly is seen to have a pair of complex conjugate roots, plus or minus omega I. Therefore, a fundamental set of solutions is given by e to the 0 times either the sine or cosine of omega x. So here was our differential equation that could be a bad situation for us, and we found that a fundamental set of solutions would be sine or cosine of omega x. So a general solution to this differential equation is, in fact, some multiple of sine omega x plus some multiple of cosine omega x. Now that's exactly what we were trying to use as a forcing function. I'm sort of sweeping under the rug, by the way, the issue of a phase shift. If there was a plus phi and a plus phi in here, trigonometric sum identities would allow us to express this as a different multiple of sine omega x and a different multiple of cosine omega x. So it really wouldn't be a different problem. Now, past experience tells us if the forcing function actually belongs to the set of solutions of the homogeneous linear equation, we might try adding some sort of multiple of x to the expression. So instead of just something times the sine of omega x, maybe ax plus b times the sine of omega x, and similarly cx plus d times the cosine of omega x. So in our potentially bad situation, where c was a omega squared and b was 0, we reduced the situation down to this. Y double prime plus omega squared y is some combination of sine and cosine of omega x, where this omega is exactly the same one that appears here. And we're proposing as a solution ax plus b times sine omega x, cx plus d times cosine omega x. Well, then we start computing. Here's the first derivative, here's the second derivative. Okay, it's a bit of a chore, but it's just differentiating. Okay, so if I wanted to compute yp double prime plus omega squared y sub p, well, I would take omega squared times y sub p and add it to all of this right here. A lot of stuff simplifies down. Very many terms actually cancel out, and you simply end up with negative 2c omega times the sine of omega x plus 2a omega times the cosine of omega x. So if we were to set negative 2c omega to be k1 and 2a omega to be k2, we would in fact find our particular solution. Okay, remember the goal here was to let this yp actually solve this differential equation with this forcing function. And since we wanted this to be k1, that's easy enough. And we wanted this to be k2, also easy enough. So we simply have to let y sub p be k2 over 2 omega times x sine omega x minus k1 over 2 omega times x cosine omega x. So our intuition was essentially correct. When our forcing function belongs to the set of solutions to the homogeneous equation, we get around that by throwing an x in front of the sine and also an x in front of the cosine. As a first example, let's find all solutions to this differential equation. From experience, we know that we need to begin by considering the complementary equation. Setting the forcing function to be 0 will allow us to find general solutions to the homogeneous complementary equation. Well, it has complementary polynomial 2r squared plus r minus 3, which actually factors quite nicely as 2r plus 3 times r minus 1. Therefore, a fundamental set of solutions is given by e to the x and e to the minus 3x over 2, because the roots of that complementary polynomial were 1 and negative 3/2. Now, the forcing function has two trigonometric functions that have different periods and phase shifts, so we are going to have to use the superposition principle and attack each one of them differently. So let's go ahead and do that. First, what we have to do is find some y sub p, so that if we were to use it in the differential equation, we could produce that first term of 2 sine 2x plus 1. But we've already done a lot of very general work deriving formulas. Okay, whenever we have ay double prime plus by prime plus cy equals something times a sine of omega x plus phi plus something times cosine omega x plus phi, we know that our particular solution is given by some multiple of a sine of that same period and phase shift plus something times a cosine with the same period and phase shift, where a and b have very explicit formulas that we worked out. So all we have to do is match this to the information we have. We have values for a, b, and c. They are 2, 1, and negative 3. Okay, we also know that omega is 2 and phi is 1. Also, k1, the number in front of the sine function, is 2. And what value do I have in front of my cosine function? Well, 0, because it's just not there. So we have k1 is 2, k2 is 0, omega is 2, phi is 1, a is 2, b is 1, c is minus 3, and we just have to plug that into all of this. So here was our proposed solution, and taking all the values for k1, k2, abc, omega, and phi, and plugging them in, we get these expressions right here. So that works out to being a is negative 22 over 125, and b is negative 4 over 125. So we actually found that in order to produce a forcing function just of a sine of 2x plus 1, we actually do need a sine and cosine in y sub p. But we're not done. We also need to find some other particular solution so that if we were to use it in the differential equation, we could produce the cosine of 3x minus 1. So we do have a formula. Here it was. Whenever ay double prime plus by prime plus cy equals k1 times the sine of omega x plus phi plus k2 times the cosine of omega x plus phi, we just use a particular solution to be something times a sine with the same period and phase shift plus something times a cosine with the same period and phase shift, where we have nice explicit formulas for those coefficients, capital A and capital B. Now in this case, k1 refers to the multiple of sine, which is 0. There was no sine term here. k2 is the multiple of cosine, which is 1. Omega is 3. Phi is negative 1. A is 2, B is 1, C is minus 3. So we're just going to plug those into here and see what happens. So we have our second proposed solution to be something times the sine function plus something else times the cosine function. But if I take all the values from the previous slide and throw them into the formula we've already worked out, we end up with A being 3 over 450 and B being negative 21 over 450. So here is a particular solution that will produce the cosine of 3x minus 1. So overall, solutions to the differential equation are given by a general solution to the homogeneous complementary equation, plus a specific solution to the first trigonometric term, minus a solution to the second one. We found a particular function that generated a cosine of 3x minus 1, so we do have a minus sign we need to throw in front of all of that. So here we have a general solution to the complementary equation. We already found a fundamental set of solutions to be e to the x and e to the minus 3x over 2. So any solution will be some linear combination of those two. Here is the particular solution that generated our 2 sine 2x plus 1. And now I subtract the particular solution that generates the cosine of 3x minus 1. Next up, another example. Let's find all solutions to y double prime plus y prime equals 2 plus sine x. Well, we proceed pretty much as we did before. The complementary equation is y double prime plus y prime equals 0. So the complementary polynomial r squared plus r has two roots that we find quite quickly, 0 and negative 1. So a fundamental set of solutions to the complementary equation is given by e to the 0 and e to the negative 1 times x. Now thinking ahead, the general solution to the complementary equation can be written as a linear combination of e to the 0, which is just 1, and e to the minus x. So here is a general solution to the complementary equation. Now we can turn our attention to trying to generate that forcing function of 2 plus sine x. Again, we're going to need the superposition principle. Okay, the forcing function has two different terms, a 2 and a sine x. Those are going to be handled with different techniques. Now that first term is just 2. This is a polynomial of degree 0. Okay, now earlier techniques, a polynomial forcing function, or honestly just sort of staring at it, if I want y double prime plus y prime to be 2, we could just take 2x. The first derivative is 2, the second derivative is 0. Great. So there is a term that if used in the differential equation will produce 2. Now the second term, sine x, we can create using the formulas we derived earlier. When ay double prime plus by prime plus cy is some multiple of a sine and some multiple of a cosine with the same period and phase shift, we set our particular solution to be capital A times a sine and capital B times a cosine of the same period and phase shift, where capital A and capital B are quite explicitly computed as such. Now in our situation here, we just have to go through and pull out values. A is 1, B is 1, C is 0, because I do not have a y term. K1 is 1, because I wanted to get sine x. K2 is 0, because I don't have any cosines. Omega is 1, and there is no phase shift, so phi is 0. So we just have to take these values, plug them into A and B. So this was our particular solution to generate sine x. Once we go ahead and compute capital A and capital B using all of those little values into that big giant formula, we'll just get A is negative 1/2 and B is also negative 1/2. Therefore, yq is negative 1/2 sine x minus 1/2 cos x, and you can factor that minus sign out as such. So finally, a general solution to the differential equation can be given by a general solution to the complementary homogeneous equation plus some term that generates a 2 and some term that generates a sine x. And now let's find solutions to 4y double prime plus y equals the sine of x over 2. As we typically do, we're going to begin by finding a fundamental set of solutions to the characteristic equation, 4y double prime plus y equals 0. So we set up the characteristic equation 4r squared plus 1 equals 0, and we find that it has two solutions, plus or minus 1/2 I. So a fundamental set of solutions is given by e to the 0x times the sine or cosine of x over 2. In other words, just the sine or cosine of x over 2. So therefore, a general solution to the characteristic equation is given by a linear combination of sines and cosines of x over 2. But that's exactly what we have for a forcing function, a sine of x over 2. So we're going to refer back to our other formula. When we have y double prime plus omega squared y equals some linear combination of sines and cosines of omega x, then we set our particular solution to be this right here. We worked through the details earlier in the video. In order to make this match our differential equation, we should divide out the 4, okay? Because specifically here, y double prime has a coefficient of 1 in front of it. In our equation, it's a 4. So if we divide everything by 4, we get y double prime plus 1/4 y equals 1/4 times the sine of x over 2. And observe, omega is 1/2, which makes this omega squared. So we're going to use k1 to be 1/4, the number in front of the sine function that we want to get for our forcing function. Okay, k2 is 0 because there is no cosine term. And then referring back to this formula right here, since omega is 1/2, we get yp is negative x over 4 times the cosine of x over 2. So what is a general solution to our differential equation? We begin with a linear combination of the two elements of the fundamental set of solutions to the complementary equation, and then the single particular solution to generate the forcing function that we wanted. Altogether, what have we covered? To find a particular solution to a second-order linear differential equation with constant coefficients where the forcing function is some combinations of sines and cosines of the same period and same phase shift, there are two basic scenarios to worry about. First, the trigonometric forcing function is not a solution to the complementary equation, or it is. And that can only happen if the complementary equation can be written as y double prime plus omega squared y is 0, where omega is the same omega from these forcing functions here. Either way, there is a formula, nice and explicit, for how to construct a particular solution to generate the forcing function you want. Those formulas appeared earlier in the video, and we're not going to recopy them here.